First thing first, all mobiles go in your pocket, in your bag, something like that. No mobile device in your hand. Computers is fine, but yeah, all the mobiles go away, please. Okay? I had an incident the other day at kind of knocks me off my game, so. So let's bring up the notes, see what we are dealing with, and also I'm gonna take a look at what we've talked about last time, quick review. So that's what we are going to do. So we talked about the overall object terminology, understanding what is object orientation, the three pillars of object orientation: polymorphism, inheritance, and encapsulation. We said polymorphism is doing the same thing in different ways. Encapsulation is putting the data and the behavior related to data together. What was the other one? Inheritance is reusing design. We talked about modules. We said when we have modules are essentially things that are related to each other, packing it in one file, and have several files in your development environment. In our case, soon we're going to learn, each class that we have will have a module of its own. So, and that's how we are going to design. We talked about how compiler works, and we brought us the picture, and we understand that when you have 5 files in your application, 5 modules essentially in our application, each file, when the compiler is compiling, is called a translation. A translation module, and that translation module has a scope of its own, which means it gets separated, it gets compiled separately on its own. If you have 5 files, your compiler runs 5 compilers and 1 linker, essentially 5 times the compiler runs to compile each file. And each file is compiled as if other files don't exist. So things that are defined in the other files are not accessible to the file that is being compiled, unless you promise that you're going to bring them on later in your linker using header files and function prototypes and things like that. And when all the compilation is done, the linker put everything together, make sure that the promises that you made are actually kept. When everything is good, then executable actually gets created, and life is beautiful, and you start debugging your program. And that was that. And now we're going to actually start talking C++. So we are not getting into object orientation yet. First, we're going to talk about types, overloading, references, and things like that, understand exactly what they are. Then we're going to spend quite amount of time on what we call dynamic memory allocation to understand exactly what it is. So, let's create a program. So in here, I'm going to include IO stream. IO stream is essentially where all the input and output streams are at. You had standard input output in C. You have IO stream in C++. Why they call it stream? Because all these devices are like stream of characters are coming and going. That's what they call it, IO stream. So input stream and output stream. In that IO stream, 2 objects are defined. One is called cout, the other one is called cin. These 2 objects are essentially, put your cell phones to mute, please, thank you. So there are 2 things created in IO stream, 2 objects. One is called cout, and the other one is called cin. These 2 objects represent themselves, impersonate console output and impersonate console input. So anything you insert into cout is going to appear on screen. Anything that you extract from cin is going to come out of your keyboard. That's how C++ works. Everything is done with action, and it's polymorphic. because it's polymorphic, the action of insertion and extraction is actually a polymorphic thing. And I'll explain it to you in 2 seconds. So int main, return 0. We don't put void inside here anymore. If you don't put anything, that means void, unlike C language that you put void in there. Okay, so C out is the console. If I say C out, 03 September 16th OOP244NAA, I can actually do it this way. Let's put it like this. So I can say over here, I can say 3. Then I'll put September. Then I'll put September like that. Then I'll put 16. Then I'll put OOP. And then I'll put 244. Then I'm going to say go to new line. So what happens is that the action of insertion, as you see, these two little thingies that you have, is called insertion. And by the way, the C out is what we call in a namespace. I'm going to tell you exactly what a namespace is in 2 seconds. So in here, I'm going to say using namespace std. I'll tell you exactly what it is. So the action of insertion is a polymorphic one. So when you want to insert 3 into C out, you don't need to mention as %d anymore. There is no such thing. You simply say 3, and because it's polymorphic, it knows what is inserting. Doing the same thing in different ways. The second one is a C string. The third one is an integer. Again, C string, integer, and the other one is an end of line. Now, \n and end of line are essentially the same thing almost. \n means new line, end of line means new line, and make sure the user sees it. The reason is that sometimes you are in environments that there are shared consoles like SSH that you connect to Linux, and hundreds of people are connected to Linux at the same time. So when you print something on a screen, not necessarily you will see it. It will show it when it's good and ready. Okay, so \n goes to new line, but something may not be shown on a screen. So end L means not only go to new line, but flush it over the user's screen so user can see it. That's what end L means. So end L is to make sure, so if you are asking for someone's name, end L means flush it. Go to new line and flush it so they can actually see it. Okay? So this actually shows, and if I want to actually, so in here, if I have an integer age, and I want to know what is someone's age, and I'm going to say C out, hello, how old are you? And I'll go to new line, and I'm going to show a prompt. Now I'm going to say end L, and then in here, I'm going to say extract from C in and put it in age. I don't need to mention that it's an integer. Extraction means extract. It looks at age. What is an age? An integer. So it will read an integer. You don't need to tell it to read an integer. It's polymorphic, doing the same thing in different ways. Or I can say something like this. Int name. Oh, hell, not hell, hello. So this is what I'm going to do. I'm going to say, C out, what is your name? And then I'm going to say extract from C in and put it in name. I don't need to mention what. Of course, I have to write the name properly before I do that. So I don't need to mention what is name. It will know what is name, and it will read it. Why is it giving me that error? I don't know. We'll find out. And then I'm going to say hello, name. How are you? How old are you? Age, and I'm going to say C out. Cool. So you are age years old. New line. Still, I don't know why I'm getting that error. We'll find out. Oh, because I said int. I'm an idiot. Character. Okay, character name anyway. I don't, integer, doesn't make sense. Okay, are we okay with this? So it's just a demonstration of a polymorphic language. As you see over here, extraction is extraction for whatever you are getting. It knows what you're getting. Again, you have to remember, this is C++, which means when you say name, you put name. When you say age, you put age. It doesn't, if you say age and you start entering an integer, it goes bananas, okay? Those that the foolproof entry we're going to learn later. So C in and C out are very shy objects, okay? If you ask them to do something and you do something else with it, it's going to do a silent treatment with you. It's not going to talk to you anymore. You have to apologize and then do it again. So literally, you have to say, hey, I'm sorry, let's start over, and then you do it. So that's essentially what the foolproofing is. We'll see it soon, okay? But you don't say sorry. It's another thing, but I'll tell you what it is. So essentially, this is the polymorphic way of writing program in C++. So essentially, that what happens if I write over here 3 years later. So what? Oh, let's put this one at right and this one at left and move this to right. So why you're, oh, so I'm an idiot. I put over here new line. I don't need to put a new line. So let me fix. Immediately, see, I wrote 3 lines of code and I made a boo-boo, okay? So I'm not supposed to do that. So I'm going to take this end L out over here. And I'm going to take the end L out over here too. And I'm going to rerun the program. So I'm going to stop. Somewhere debugging it says stop. Where is it? Oh, I control F5'd it. I'm going to say control C.
What are the arrows denote? I'm sorry, I missed it.
This one?
Yeah.
Insertion, extraction.
Oh.
I'm inserting into C out. I'm extracting from C in. C out is a representation of console. C in is a representation of keyboard. Okay? Console in, console out.
Yes.
All right? So now let's run it one more time, see if it runs better. So,
Very like Linux.
all right. So, come on today. Keeps going, keep going. There you go. So what is your name? Well, my name is Fardat. Now it's going to say, hello, Fardat. How old are you? And I'm going to say 59. And I'm going to say, cool. So you're 59 years old. Are we good?
It's basically just like Linux, all of it.
All right.
Yeah.
We good? All right. Okay, so that's a polymorphic language, as we mentioned. So, types. The types that we have, they're all exactly like C language. So we have character, we have short, we have int, we have long, we have long, we have long, and then we have long. I'm joking, just long. No more than that. So we have only 2 longs. Okay. So long, and so these are all integers.
Long doesn't.
Yeah, no, just 2 longs. Okay. So character, short, int, long. Go read it. Okay. I'm not going to write it over here. Character is exactly 1 integer. Okay. It's the smallest integer that you have. There is no such thing called character in C language. If they told you it's a character, they lied to you. Characters are just an integers that are big enough to hold the ASCII code of a character. That's why they call it a character. Yes?
We've been lied to.
Oh yeah, I know. Well, you've been lied to badly. Okay? So seriously, characters are nothing but integers. Okay? The only reason that they call it character, so essentially, if I write a code like this, so this one is, I'm going to say A, polymorphic, polymorphic, insertion and extraction. By the way, my English sucks. If you say I'm making spelling mistakes, my apologies. Fix it.
Polymorphic? It seems just like Linux, where you just
It's polymorphic. Polymorphic means many shapes, which means this and this are integer and string. It's the exact same thing. It means insertion is working the same way, printing different things in the same way, therefore the definition of polymorphic.
Okay, so you can insert integers or strings, and that's why.
Anything. Okay, so character. So we were talking about characters. So If I have a character over here, CH, I can say character CH is equal to 65. And when I say 65, if I say C out CH, what it's going to print for me is essentially what? Where's the output? Here. A. Because 65 is the ASCII code of A. And if I go CH plus equal 3, and I say C out CH again, oh, come on, you can do it. All right, and voila. So what I'm going to see now is going to be D. Are we okay with this? So if I told you what are the types that we have, what are integer types that we have, smallest integer type, character is smaller, then short, then int, then long, long. Are we okay? Are we okay? One?
Double?
Are we okay? Integers, scalars. I'm not talking about real numbers. Okay? So int character, short, int, long. Are we okay with this?
Yes.
All right. So, pardon me? Yeah. Go read the notes. So you think I memorized all this? No, I have a cheat sheet over here, and I'm just reading it and telling to you. It's right in your notes. Okay, go read the notes. But in the notes, it doesn't say that, okay. No.
And Del
Okay.
needs to be at the end of every input read and write.
I'll talk about the bool. Give me 2 seconds. We got down to this point. Then we have real numbers. Real numbers are float, double, and long double, and long. Again, no long, there's one. So float, double, and long double. Okay, these 3 things. Now, these floating point numbers are very tricksy numbers. Okay, let me just write over here character, Alt F-A, B, so I'm going to say over here, come on, char.cpp. By the way, when I talk about character, it's C. It has nothing to do with C++. I'm doing C out. Oh, by the way, another thing that I could do over here and I forgot to do, got distracted, is you can actually say C out. If you cast, how do we cast in C? I can say int CH, right? Yeah. And it actually prints that. So I'm actually telling to, but that int thingy in C++, they kind of move the parentheses to the other one. So they don't do it like this. They do it like, it works. Because it's C, it works. But you can do it like this. In C++. Same thing. Okay? Let's do it that way, C++ way. So if I actually do it like that, you will see that the outcome is going to be 68. Right? So it actually shows what it is, shows its nature. Let's put this as the other one, C, and I'm going to...
Sorry.
Be sorry for nothing. What's up?
Does it add byte by byte when it goes from 65 to 68? The character becomes...
What are you talking about? I just told you there is no character. Why you're saying character?
So then,
Why you are saying character?
because every character is...
There is no character. It's 65.
No, okay.
But what happens? But what happens is that when you see outing it, when you're inserting it into C out as a type character, you're telling to C out, show me the shape of 65. That's capital A.
With the ASCII...
There is no character.
Sure.
Got it? There is no character, people. We don't have such a thing as character. If you ask the compiler, show me the shape of 68, so let's put it this way. Give me 2 seconds. So essentially, I can do this. Did I copy? I think so I can do this. Right? And in here, I can do this. So now if I run this program, obviously I'm going to see. Got it?
Yeah.
So there is nothing called character. I'm just saying now the ASCII code is 65 and show me the character version of a 60 something. Yes.
Instead of 65 and put an A and then plus.
Yeah. So essentially what happens is this. Okay, because we cannot memorize ASCII codes, they created single codes. So they say, if you put a single code over here, and you write over here A, I'll remember what is the ASCII code and I'll give it to you. So there is no A. Single code A, single code is literally 65. And if I run in, actually, thank you very much for that. So if I actually do this, what I would see is again, the exact same thing. Because single code A essentially means 65. So if I told you print characters from A to Z, all you need to do is say for CHI equals to A, and I less than or equal to Z, and I plus plus, it will print all of them for you. We good? Yeah. All right. A good question for a quiz. So we are in OOP244 September.
What's the question exactly?
I'll give it to you in a second. Let me write down over here. OOP244 September 16th. The question would be, write a program that prints the ASCII table. Done.
Oh, the whole thing?
ASCII table, sure, it's a loop. Starts from 1, go up to 2. Start from 1, go up to 128. Those are the printable characters, right? And just print them one by one. And I didn't say hexadecimal, just ASCII table. So all you need to do, you're going to show the characters and show the code right beside them.
It's 255 extended.
Write it down and see what it is. Go practice at home, and then when you're coming to the quiz, you write the proper one for me. Okay? We good?
Sure. That's easy.
All right. So floating point numbers. Floats. F is equal to. Floating points are a very tricksy thing, okay? Floating points are not called floating, like they're real numbers. And they call it double because, not because it's double size, it's double precision, okay? So what does it mean, precision? It means a float number can handle 7 digits only, ignoring leading or tracing zeros. So 1, 2, 3, 4, 5, 6, 7, 0, 0, 0, 0, 0, 0 is fine. Or 0.000000, 1, 2, 3, 4, 5, 6, 7 is fine. If it becomes 1, 2, 3, 4, 5, 6, 7, 8, precision is lost. The number is not precise anymore. It doesn't matter where this 1, 2, 3, 4, 5, 6 is, because the number of zeros before and after translate to the amount of exponent it's adding. 10 to power minus 4 or 10 to power 8. That's the number that goes. Zeros before and after. It's the significant digits that actually dictates the precision. We don't need to understand it. We just need to know what it is. Okay? And for doubles, that's 15. So 15 digits back to back, leading zeros or trailing or leading zeros, irrelevant. Floating point where it is, irrelevant. It's only the 15 numbers. So as long as you have 15 digits, the precision is sharp. Other than that, it's bad. It's going to go bad. Okay? That's why these things are never supposed to be checked for equality. You can never, ever, for sure, say that a double value A is equal to a double value B. You cannot test that. You can have a logic that goes through several different things, and logically, the value of A and B are 2. But when you check it with an if statement, it gives you false. Why? Because one is 1.9999999, the other one is 2.000000. Logically, they are both 2. But the bit pattern is not the same, therefore the comparison fails. If you want to test to see if 2 real numbers are the same or not, what you need to do, I know it's going to freak you out when I'm going to tell you this, but that's a mathematical thing. So the difference between the two the absolute value of the difference between the two should be less than the precision you want. What does it mean? It means if it's important for you to have 3 digits after the decimal, it means your precision is 0.0001. Difference bigger than that, it means not equal. Difference is smaller than that, it means good. Now do the difference, see if the value is less than that, you're good. That's how doubles work for precision. So floating point, float f, so this is okay, 0.123456 this is okay. Float f2, 0.12345678 lost value. Okay? Lost precision. Yeah, lost value. It's going to lose some value. Something's going to get lost over there. And the same thing for, so probably it's going to lose value. They always say that, probably. Okay?
Isn't it the other way around?
Doesn't matter. Where 0 is, it doesn't matter. It could be this. Let's put it like this. This is okay. These values are all.
No. I'm saying, isn't it the other one that is okay and the other one that is losing value?
This is okay. The first one is okay. Because it's 7 digits. Leading zeros, gone. Do you have 7 digits? Yes, you're good. You follow? Remove this leading and trailing 0. So let me tell you what values are okay. Oh, come on. Six, 7. This is okay. 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 These are all okay. If 1 digit is added over there, it becomes 1, 2, 3, 4, 5, 6, 7, 8. In any of these, you lose value. Got it?
So I'm just saying, mathematically, that's a different number and we don't disregard it. But here in computer science, we do, right? Because zeros after the dots.
No, excusez-moi.
And
Mathematically,
yeah.
these are all okay. Computers is mathematics. Don't insult maths. Okay? Mathematically, these are all okay. Mathematically, when you make the 8 more, you don't have enough space to hold the digits anymore. So therefore, some of it's going to throw away. Mathematically, you have enough bits to hold 7 digits. If it goes more than 7 digits, it doesn't fit. Yes?
What if the 0 is in between the digits, like 1?
Then it's counted as, I said, leading or trailing. So this is not okay. This is not okay. Now you don't, this is not leading, it's halfway through. Okay?
What if it was 1 point and the same?
It doesn't make any difference. And this is okay. And this is okay, and this is okay, and this is okay, and this is okay. These are all okay. Got it? Why? Because all these values only change, because essentially, what is this? What is this 1, 2, 3? This, when you actually put it in scientific notation, it's 1.23456 multiplied by 10 to power what? 2.
Which means it needs
100. So 10 to power 2 multiply, I cannot write it over here. 10 to power 2, right?
Yeah.
Right? So E2, let's put it this way. It's multiplied by 2. Where I put the decimal point only changes the 2 over there. If it's this one, oh, this actually doesn't mean anything because all the zeros are gone. So these are all okay. Yeah.
It must store the exponent.
Yeah, so this one essentially becomes literally multiplied by 10 to power minus 4. Therefore, that exponent, it changes, not the value. Got it? Okay. Again, try not to understand it. That goes to math. It's not what we're going to do. Just remember, leading zeros, trailing zeros, the digits less than 7, you're good. If you're double, less than 15, you're good. Okay? Long double, I don't know. I forgot. Go ask ChatGPT. It's going to tell you. I forgot what it is. Okay? It's much bigger because you have a bigger. No. You good? All right.
Well, 7.
Save the real numbers. Anyways, floating points, real numbers, or whatever. Now, in C language, now we have the microphone. The person with the microphone, answer please. In C language, what is true?
Sorry?
In C language, what is true?
True. True is represented by 1 and false represented by 0.
Wrong, pass it.
Okay.
In C language, what is true?
In C language, what is true? Anything else than 0?
Thank you. That's it. You got 1% for your midterm. Remember, pass it through. Okay? Sit closer to each other so we can give that microphone easier pass along. Okay? So anything but 0 is true. So if I say if 1.56 and close the parentheses, that means true. It means the result of any type of operation. Is it non-zero, it's true. The only unique thing that is false is 0. Are we clear on that?
Yes.
Are we good? Fantastic. That freaked people out. Okay, you say, no, true should be 1, not 0, right? Not anything else. That's why they created type Boolean. We now have in C++ a type BOOL, bool. What does it do? It's 0 or 1, which means if you put any value other than 0 in it, it changes it to 1. Okay? So if I say bool, so I can say bool, and then they created 2 literal values, true and false. True all lowercase means 1. False all lowercase means 0. Okay? So you can actually have something like bool, not vool, bool, condition, let's say. Now you can say condition is equal to true. It understands it. You can say condition is equal to false. Understands it. But if you do cout, the true nature comes up. Oh, stop. It's compiling, son of a gun. Okay. Sorry, I love to have a full keyboard, but this is easier to carry. So now, if I say over here, condition is 1.345, or something like that, that's what happens. So if I run this beautiful program of mine, 3 years later, when it compiles, the outcome will be, got it?
Yes.
Okay. So, when the language is generating a condition result for you, it's always 0 or 1. But when a condition is checked, 0 is false, anything but 0 is true. Which means, if I write integer a is equal to 10 greater than 20, what is a? What is a?
True.
You say true? 10 is greater than 10?
Oh,
Oh, okay.
sorry.
So this is a statement. Remember,
0.
operators are operators. They return values. It doesn't matter if it's condition or not. You can say a is equal to 10 greater than 20. Is that a true statement? What does it mean? The value is 0. Therefore, a is 0. If I say a is equal to 10 greater than 20, or if I do this, Oh, not that, not that. This, okay, yeah, there you go. Now if I run this, I'm going to get build error because I have two integers. Control F5. Got it?
Yeah.
Now we understand what Boolean is, what conditions are. Are we okay? Yes, sir.
So when you're doing conditional statements like that, I guess the language generates the value for you, and that's why you're getting the 1 or the 0.
Yes, exactly, exactly. So the answer was that because the language is generating that. And that eliminates lots of, like for example, another good quiz question is this. Write a program that counts the number of values greater than 20 in an array without an if statement. I want to count how many things in an array is more than 20 without an if statement. How do I do that?
You just have a condition that checks it, and then if it's 1, then you add it to a variable.
That's it. So all you need to do is to write the condition. The condition is going to return true or false, which is 1 or 0, right? Have a variable that is set to 0 and add it to that. So while the loop is happening, you say int cnt is equal to cnt plus equal the condition. If the condition is true, 1 will be added. If it's false, 0 will be added. Therefore, you're counting it, right? Without an if statement. And it's hundreds of times faster, not hundreds, much faster than an if statement. So if you're writing a programming thing for a game and you want to count something, writing an if statement is very slow because it has to check a condition. If the condition is true, it continues. If it's not, it has to jump to the next state. These things are time consuming. That's faster. Nothing to do with C++, but hey, we good? So ABC, oh, I forgot C. So that's C. And now we have D, bull. We okay?
Does it have and, or, NAND, NOR, XOR?
That's C. Go back to C. Of course we have ands. That's C.
Okay.
And we don't have a NOR. It's not Boolean algebra, it's conditions. We have and, or, not, and that's it. Yeah.
They hit them over the bed in my C course. No.
All right, so we have the Boolean. Now compound types, you've done it in C language. Please go read it. I'm not going to. Compound type is essentially a type that is made out of other things. Okay, so you have a structure, you have 5 integers in it. That's a compound type. You just created it. And in C++, when you create a structure, it immediately becomes a type. You don't have to repeat struct. You say struct record, you put 3 integers. If you want to create a variable out of this, you just write record A. You don't need to say struct record A anymore. We call these compound types. Okay? So I'm just going to bring the example that we have in the notes, and I'm going to put it in here so you see what I mean. So when you write something like this, it's a compound type, and if you want to actually create an instance out of it, you simply say transaction T. You don't need to mention struct transaction anymore. These are called compound types. We good? You okay? Oh, God. don't know if it's like, for you it's like that or not, but in the morning I type perfectly. As we go later at night, I start typing very badly. Anyway. So that's that. We know all that thing. We have in the notes auto keyboard, auto keyword, auto, A-U-T-O. I don't want you to study it. I don't want you to know it. Completely forget about it. You've never seen it ever. There is no such thing called auto. That's OOP345. In here, it just confuses the heck out of you, okay? Never, ever in this class you are to use A-U-T-O, ever, okay? We don't need it. When you write a prototype, what are you doing for a function?
Oh,
When you write a prototype, what do you do? What is the purpose of a prototype?
Oh, I'm blanking. I pass.
Nah, you know what it is. You know. Okay. You know what is the purpose of a prototype?
Define in the header file.
So we use the prototype in a header file to it's not defined. Define actually means something in C. I know you know the answer. You know what it is? So in English, you don't need to put any buzzwords for me. Just tell me what is the purpose of a prototype.
A prototype is just the function description.
Yeah, function description introduces the function to other modules. Right? Right?
Yeah.
Yeah, so keep it. So I actually can pass it my friend over there. He's gonna be the next victim. Okay, so this is what we're gonna do, right? We're okay down to this point? Yeah. So okay, that is called a declaration. So when you write a prototype, you're declaring something. Definition is to actually write the function.
Yeah.
All right? All right? But sometimes declaration and definition go together. How? When you write a function at top of another function, you don't need to write any declaration. You can just use it because it's at the top, right? So a definition can be a definition can be a declaration, but declarations cannot be definition. When you declare, you're just writing a prototype, okay? So later we're going to learn how we can actually write a prototype for a variable. You can even write prototypes for a variable. So you have something, you want that thing to be accessible somewhere else. Remember global types you said? They lied. It's not global. When you write a variable at the top of everything, it's only accessible in that file, not the other files. How can we make a variable be accessible across all transaction units, across all the modules? That's how we write a declaration for a variable. We'll learn later, okay? Read all the stuff and then come with questions. So, what do I do?
swipe up on your keyboard.
I hate touchpads. Very thick skin. Like, I can never make that right thing that you do. Like, every single tab is double, so it's a bad thing for me. I hate it. I wish I could disable it, but yeah. I need to know how to do it. I'm going to learn it soon. Okay. So, scopes. What are scopes? Scopes are where variables are visible. Okay? What was your name?
Haldane.
Alden?
Ali is fine.
Al.
Ali.
Ali. Oh, Ali. Okay, Ali. So, Ali, okay? So if I say, Ali, give the microphone to your friend, Ali will do it, right? But if this is 1081, if I'm in 1079, over there, I say, Ali, give the microphone to your friend. Nobody's going to answer. Why? Because I'm not in the same scope of Ali, right? Do we understand this? Okay. Now, please listen to me carefully. We have different types of scopes. You see that something thingy over there? Okay. We used to call that the global, right?
Yeah.
It's not global. It's file scope. It's only visible in this file. If I have 5 different files in my compiler, it's not going to actually show it. So you still don't know how to create global. Okay? That's a file scope variable. A global scope variable is a variable that it has a prototype what we don't know how to create yet. So we don't know how globals are done, but they are possible. Essentially, a file scope has the potential to become global if it has a declaration. If it doesn't, it just remains file scope. We're good? Then we have function scope, value in foo. It's only visible in foo. When I get out, it's not going to be accessible to any other, right? Same thing as condition over there, correct? Same thing as first A. The second A in 21 has a block scope. So it is not in conflict with the other A because it's in an inner block. But the problem is that in that if statement at line 21 and 22, it is impossible to access the A outside because A inside is shadowing it. It's just common sense. Because they have different scopes, it's allowed. But because you have an A inside and an A outside, in here, this A has nothing to do with that A. After this scope is done, it dies. And the rule is that any scope, when it's gone, all the variables are gone. Okay? So, go read the thing, the notes. You will see in the notes it says, maybe I should bring it up for you.
So that's different in C, right?
So, no, it's exactly the same. Global scope, we don't know. File scope, I told you. Function scope, I told you. Block scope, I told you. Class scope, we don't know what the heck is a class, so I'm not going to say it now. We'll talk about it later. Yes, sir.
If we don't initialize A in the inner function, does it still, so we cannot access the outer A if we just don't initialize A?
What? Initialization has nothing to do.
Defining.
Give me line number.
If we don't,
Give me line number.
21, let's just say A.
If you just say A, it's A. It's the A that is outside. It gets it from the outer block.
Yeah.
Of course, you know that. We've done that, right? But if you create the variable that you have outside, it shadows it. And they have nothing to do with each other. We good?
Yeah.
All right. Scopes are done. So in here, this is going to be EF scope dot CPP. So the only thing in here that is C++ is class scope. Other than that, everything is C. Got it?
Yeah.
In here, everything is C other than that class. Questions? Suggestions? Objections? Okay.
There's a way to set these to global variables. To create a definition.
I want to create a function that draws a bar for me. So kind of draws a line for me. So if I want to design something like that, what do? I write integer. Not integer, void. Yeah, void, let's call it bar. I'm driving a bar, right? So first of all, I need to see with what character I want to actually show it, right? What character I want to use to draw the bar. So I need some kind of a character to fill the bar with. Then I need to somehow show what is the size. So size is the next one, or length. You okay with this? So now I can actually do it. I can write over here for integer I set to 0, I less than len, and I plus plus. I can say C out, print the fill, and C out and L, right? We good? You okay? So I can write over here bar. 1 point, flashing over a projector makes the thing fade. Yet if you turn the flash off, it's going to be a much better picture because it's reflecting light. You do the flash, it's going to make it matte. I strongly suggest. So, photography point. Okay, bar. Okay, so now if I write over here, I want the length of 30. Oh, so no. Like I want to do dash and length of 30. Bar is displayed for me, right? Good?
Could you define fill in the void?
Excusez-moi?
So instead of putting bar and then put the quotations, can you already declare that the fill should be the bar? Should be the dash?
We'll come to it.
Is this hurting you?
Pardon me?
Hurting you?
The-
Is this hurt your eyes? Is this hurting you when I do
Not at all. I was giving you a pointer so you have a good picture over here. That's all. Flash on projector doesn't work. Projector, TV, flash is not a good thing because they are actually. Anyways, you know better. Okay, so, but when I don't have a length, I want it to be 79 characters to go all the width of the whole thing. Okay? So if I want to do that, now I'm going to actually make it a normal size so we can actually see what I'm talking about. So if I want to do that, I have to say void, say bar 79, and I have only a character fill in here, right? I don't need anything else just to show what I want to do. And I can use the bar up there. I can reuse my code and say pass the fill with 79 characters, right? So now I can say bar 30 or I can say bar 79. Or bar 79 with a say like that. So if I run this code now, this is what I'm going to see. We okay? Are we okay? In C++, we have polymorphism, which means you don't need to name that differently. Just call it bar. It knows which one you're calling. From its arguments. You're saying I want a bar with the characters? Sure, I'm going to call what bar with the character. It's polymorphic, doing the same thing in different ways. That's called function overloading. And you can keep doing that. I can actually write something like this. Now I'm going to say, if I say just bar, now because the source code, because it's the same thing I'm doing, I'm just calling the same thing. But you may do completely different things, completely different actions. Like if we were actually programming flying of a helicopter and flying on an airplane are completely different beasts. So the interior may be different. In this example, I'm just doing the same thing. So now in here, I can actually say bar, say with a dash and a 79. So if you don't mention anything, I'll do it like that. Right? Oh, I should call it. Okay? So now if I run it, it actually picks the proper one automatically, the one without and all the good stuff that we have. So essentially it runs it like this. Are we good? Now let's say if I actually have a character here, have an integer here, then it's going to show a bar with underline and the length that you want. So now you can actually do, or let's put something completely different. I'm going to say with plus. Okay? So if I only put an integer, say 60, then it's going to be defaulted by plus. You good? This is called function overloading. So based on its argument, it can decide which one to pick automatically. Are we okay with this? All right. EFG overloading. But we have even better feature than this. So when you look at the first three ones, the second one is essentially calling the first one with len being 79, right? So what I can say, hey, compiler, if somebody calls my bar without a len, put a 79 instead. Easy. Now, it has the exact same effect when you run it. Even the one that is called with one argument, it's going to call the proper one. Why? Because it's going to say, okay, you want it with one argument, you didn't provide the second one, so I'm going to put 79 instead. The one that you say 30, because you said 30, I'm going to ignore the 71. Same thing over here. So bar without anything is with a dash, right? So I can say, okay, if they didn't put that one over there either, put a dash. But this one I can't do because I'm completely changing the order of arguments. Default value for the arguments can be done from right side. You cannot do it from left side. Okay? So this one has to be overloaded. There is no way around it. But that one, you can put default values instead. Are we okay? So if the logic of the function is identical, it's better to do default value. If the logic is not identical, you're doing something different, then overload. Or if the order is different. Be okay? All right. Control.
What do you mean from the right side, not the left side?
Pardon me?
What do you mean from the right side, not the left side?
It means you cannot default the fill, but put the value for. You cannot do this. This doesn't make sense. I can't do this. I cannot say bar, comma, 50. You cannot let the first one be defaulted. It has to be from right side. This doesn't work. You cannot violate the syntax, or you cannot have incorrect syntax. So you can do default values only if the syntax of the language is not, yes?
In a holomorphic way, can we have also a return function or?
No. Oh, amazing question. The signature of a function in C language is only its name. The signature of a language in C is only its name. The signature, Fardad, reboot. The signature of a function in C language is only its name. The signature of a function in C++ is its name and its arguments, not the return statement. So you can have the same name with different arguments, there are different functions. But one of them returning integer and the other one returning float, there is no, just take a look at it. From this, can you guess what it returns? No. There is a way around it. OOP244NAA. Not now.
What do you mean by signature?
Signature is what, when you write, what your signature identifies you.
Yes.
The signature of a function identifies the function. The signature of this says bar char int. Bar char int.
Yes.
Which one is bar char int? Bar char int. So it knows it's that one. This one says bar char. Bar char. Int is not provided, but I have a default value. So I pick the default. This one says only bar. It says bar. Nothing is provided, so I'll pick up the dash and a 79. This one says bar int. Bar char, that's not the one. Bar int, this is the one. I pick up this one. Signatures must match. Yes, sir.
So when you're identifying these by signatures, you're saying that these are different functions, even though they have the same name. There's
Yeah, of
different
course.
functions
So
that are-
from main's point of view, it's polymorphic. Of course, you have to design different functions. You cannot say, I'm going to write the same function and it will do magic and do different algorithms.
How does that affect what it returns then?
Pardon me?
How does that affect what it returns?
It doesn't affect anything. So the return statement is irrelevant. It's not part of the signature. Okay? Are we good? GH, default argument values.
Okay.
Good. We are at some nice place now. Now I have something amazing to share with you. I don't know about you, but I came to Canada in 1994. So as soon as I came over here, they changed my name. So I went to a factory. My name was Fardat. Okay, the very first thing the guy said, can I call you Freddie? So I was Freddie over there in the factory. But now I'm a teacher. I have power over my students, so I can say, you have to call me Fardat. Don't call me Freddie, right? But let's say that's not the case. And I say, my name is Fardat. Please call me Freddie. Okay? All right? So it's just for the sake of example. Please don't call me Freddie. Okay? But let's say I ask you that. If I tell you my name is Fardat and call me Freddie, do we have two people now? We have one person with two names, right? Correct? We can do that in C++. You can give the same variable several different names. It is the same variable, though. Let's do that. So I have integer var, and I put over here 100, right? Let's say I wanted that name that var num. So I want to give it a new name. How do I do that? If you write integer num equals to var, then num becomes a new variable. Now I have two variables, correct? I don't want that. I want the same variable. So what you do, you put an ampersand right after the type. Now, I want you to please pay attention. Did we review the pointers here? We didn't do it, right? No. Okay. So I have a routine for my IPC 144 to teach pointers. I just did it for 345 to kind of clear what pointers are, because it's a weak spot for students, pointers, right? So I'm going to take you through it too, okay? So, but for now, let's put it this way. So when you see an ampersand after int, if you call that int ampersand, I'll kill you. Name that reference what it, that ampersand what it is, and it's called a reference. Reference is essentially a new name for already existing things. So when you see an ampersand after a type, you don't say integer ampersand, you say integer reference. Clear? So I say integer reference num is equal to var. What does it mean? It means num becomes a new name for var. Therefore, I can do this now. I can write here cout var, cout num, and then I can say num plus equal 100. Now I can say cout var. And as a result, you'll see that it's the exact same thing. It actually changes the value, although I added that one. This is what's going to happen. We okay with this? We okay with this? This has a beautiful side effect, and I'll tell you what is that. First of all, you need to know one thing. You cannot say integer reference, oh, come on for that, integer reference ABC. You can't do this. It's going to give you an error. Because the meaning of reference is that it's supposed to be a new name for something. If you don't assign it to something, if you don't initialize it to something, that reference doesn't make sense. That's why you have an error. I can always set that one to num. There's no problem. Now I'm going to have 3 names for the same variable.
Is it actually a pointer or is it something else?
It's a reference.
Okay, so I can't use pointer addition.
It's a reference.
Okay.
Okay, let's not, please, that's no confusion with pointer. It's nothing to do with pointer. It's a reference, something new. We don't have that in C. Okay? Now, so what is the beautiful thing about it? This is the one. Reference intro. So what is the beautiful thing about it? Ladies and gents, with the microphone, pass to the next person, please. What is the output of the following program? It's a little bit trick question. What is the output of the following program? So I have integer var 100. Var is passed to 10. A becomes 100. A is added by 10, becomes 110. Comes back, var is printed. The output is?
111.
No. Trick question, I said. Go back to IPC and the scopes that we were talking about. Int A has a function scope, correct? It's the scope of a function, which means at line 11, var is passed to A. Therefore, A becomes a copy of var with value 100 in it, correct? Then A will be added by 10. That's 110. Then A dies, and it has nothing to do with var. Therefore, var remains 100. We good? Pass it back to the next person. We good? Wait. We good? You understand this? So if I run this, obviously I'm going to get over 100. Now if I do this, my friend, walk through it with me. Walk through it, one by one. Line 9, what happens?
So 100.
Line 11, what happens? What is A?
100.
No, what is A? What is the type of A?
A is integer.
Integer what? I just mentioned it 3 seconds ago when an ampersand comes after the integer reference.
Yeah, reference.
Thank you. I know when I put the microphone in front of people, somehow they go, they don't know what to say. But that's the case. So it's integer reference. And reference means new name for an already existing variable. Therefore, A becomes a new name for var. So when you're adding 10 to A, what's being added to by 10? Var. Therefore, var becomes 110. No need for pointers anymore. Got it? You follow what happened? Now the question is, didn't you just say you cannot just create a reference? It has to be initialized to something? That's because we don't know how the functions are called in C language. In C language, when you call a function behind the scene, this is what happens. Literally. When the function is called, it becomes void add 10 integer reference A equals to var. And then it's called. So every time the function is called, the argument is initialized by what is passed to it. Always remember that. This is 100% accurate and real. That's why I can have another thing over here. And I can say over here, add 10, num, and the function call means void, add 10, int reference. A is equal to num. And therefore, it works for all of them. So when this function, when that reference comes to being, it's a new name for var. When it's done, the reference dies. The reference dies, gone. The second time the function is called, another instance of it is getting created. This time it's a new name for num. Therefore now it's num, and so on and so forth. Are we good? Questions? Suggestions? Objections?
Just to make sure one more time. So int ampersand A over there initially is being initialized by void, and so I
Why are you rephrasing my beautiful words? I just mentioned every single argument is initialized by what is being passed to it. Always. Anything you put over here, that's what it means. You can literally rewrite it. That's why I did it. It's not going to first become anything. Literally, when you call a function, the argument is initialized by what is passed to it. Literally. There is no metaphoric stuff happening. I'm not making anything. It's literally what happens. You follow what I'm saying? That's why when we have pointers, think about it for a second. Void add 10 integer pointer. Because of polymorphism, I can do it. PTR. Now in here, I'm saying PTR. So when I say add 10, address of num, what is being called over here is void add 10 integer pointer PTR equals to address of num. And therefore everything works. You follow? Always remember that. This is literally what happens. If you don't understand something, literally write it, and you've got to say, I know what's happening now. Yes?
It's like giving a coloring book to someone for them to color in.
Exactly. Whatever color they have, it's going to come up that way. That's perfectly correct. Are we good? I'm going to end this session with a lecture that I do with OOP. Yes, sir.
If we pass a reference to the function, so it will become reference to a reference. Is it possible?
It's not a reference. Well, I'm going to say, my name's Fardat, call me Freddie, right? Then I'll go to the other class and say, my name is Fardat, call me Jack. Okay? Or I'm going to go to the other class, I'm going to say, my name is Freddie, call me Jack. If you call Jack, who's going to come? Fardat or Freddie. If you call Freddie, who's going to come? Fardat or Jack. If you call Jack, who's going to come? Fardat or Freddie. They're all the same. It's not reference of a reference. They're all the same. When you create a reference, people, the two things are indistinguishable. They are identically the same. None of them has claim. They both have claim. It's not to say which one came first and last. When you create a reference to something, it becomes a name for that. It doesn't matter which one was first, which one was next. Got it? All right. Shall we?
Can you just define all variables as global?
No. Okay. So, I wanted to give you an example of a crazy reference, but I'm not going to do it now. Crazy reference the next day. So please, actually, I'm going to write it over here. Not that I'm going to remember. Explain crazy reference. Explain crazy reference. Please remind me of it, okay? The next time I'm going for that, tell us about crazy references, okay?
I'm just going to say check your notebook for...
Oh, yeah, that's you, or you can say check your notebook. Okay, so let's start. But before we start, I have to make some preparations. Give me 2 seconds. We have till 10:05, right? Okay, it's going to be a quick lecture. This is what I do with my IPC when I haven't done it for a long time, but I prepared this for IPC 144. So since you have been there already, you're gonna relate to it. Okay. Okay. Okay, almost there. Okay. And now, first thing I'm going to ask you is to please format your brains and forget anything you know about pointers. This is a fresh thing. We're going to start from scratch. Are we okay with this?
Yeah.
We okay? So, maybe if I put it over here, I can. Yeah. This is what the memory of your computer looks like. Okay? Memory of your computer is an array of bytes. What is a byte in C language? A character, right? A character is a single byte. That's what it is. So this is what the memory looks like. So you start from 0. That's the address of the very first, that's the index of the very first byte in your memory. And it goes up to the amount of money you have in your pocket. How big is your RAM? Okay? 16 gigs, 32, whatever, 24, whatever, okay? Obviously, this number was too difficult to write, so I'm just writing the 3 digits. So when I say 101, it's 23,423,110, right? Or 101. Are we okay with this? Are we okay? All right. So this is, and the index of this array is called the address. So when I'm saying, what is the address of the thing, it means what is the index? What index it begins with. Are you okay with this?
So address?
Yeah, address is essentially index of this array, which is essentially your memory. Okay? So, when you create a variable in your C language, when you say integer var, what happens is that the system occupies like when you say integer, integer is 4 bytes. So occupies 4 bytes and tags it as var. So essentially when you, and when you say double, it picks a place that is big for a double and puts that one. So it's 8 bytes and calls it dvar. Are we okay with this? So, and essentially when you put a value in var, the whole bits of that 4 byte will be set to the binary representation of the value you are putting. Right? Yeah. And the exact same thing happens if you do it with the double thingy. Are we okay with this? Okay. Now, because of all the scopes and the things that we have, we need to be able to fiddle with these variables from outside of their scope. So having then their name is not enough. Like Ali is here. If I'm going to the other room, I have to say go to room 1081, essentially give Ali's address. So they come in here and then they're going to say, oh, the microphone is gone. Move the microphone, right? Yeah. All right? So are we good with this? Yeah. So we need to somehow deal with this address thingy. What is the type of the address? What are the type of these numbers? They're integers, right? Yeah. The only difference is that they cannot go negative. You don't have address minus 32. It starts from 0 and grows, correct? So let's create a type. So we are designing the language. Let's create a type and call that type pointer, literally. So this variable's job is to hold other things' address. That's what it's supposed to do. How big it needs to be, depending on the big, what type of environment. If you're a 32-bit environment, then 32-bit, that is 4 bytes is enough. So we assume that this is a 32-bit. If it's my computer, then it's going to be 64 bits, therefore it's going to be 8 bytes. But to be able to put big of a number that it reaches the whole end of everything, let's say 4 bytes is enough. And therefore, when I create pointer PTR, a piece of memory, exactly like an integer, will get created, and it's tagged as PTR. And it's supposed to be a pointer. Are we okay with this? Therefore, when I put some value in that variable, any value, let's say I put 102, the value of 102 goes into the variable exactly like a regular variable. But what it means for us, it means it's pointing to the address 102, right? Look at the picture. You see that? Which is absolutely nonsense. I don't have anything at 102. This is supposed to be 108. So it's supposed to actually point to a place that I have something in it. Problem is, I do not have access to the address of the variables. I just say integer age. I don't know where the heck age is. So I have to add one more thing to my language, which is extracting the address of things. Therefore, I need to say, instead of PTR is equal to 108, to say PTR is equal to address of var. So address of is a statement in C language that extracts the address of var, wherever it is, which is 108, correct? So, are we okay down to this point? Again, pointer is just like an integer. You can put stuff in it. But we want to hold the address of other variables. Therefore, we invented two things down to this point. Pointer, a type that holds the address. Address of, which something that extracts the address of anything.
So address of is a character, is gonna have hexadecimal characters, right?
Why are you going to details? It's a number. Hexadecimal, schmexahesimal. We don't care about those things. It's a number coming out. Let's not get confused with those things. It's a number that is coming out. Are we good? Yeah. All right. Now that I have this, now that I have the address, now that I can say room 1081, I need to be able to say go to room 1081 and call Ali, right? That means I need to be able to not only put values inside PTR, but also access the target of PTR, correct? So I need to be able to invent the third thing saying target of PTR is equal to 2345. And that is not setting the PTR anymore. It goes inside PTR and sees where PTR is pointing to and puts the value there. Are we good with this? Are we okay with this? Are you all asleep or awake? We good? All right. All right. So now that we have that one, we can actually print the variable, which results going to be output is 2345, right? I can print target of PTR, which is again 2345, or I can print PTR itself, which is going to be the address in which the var is, correct? Are we okay with this? Three things? Okay. Now that I have these three things, let's see if I design things properly down to this point. So let's see if we can actually do the same thing with the double. Let's see if I can say PTR is equal to address of dvar. Down to this point, no problem. When I say address of, it extracts the address where dvar is sitting, which is 132, correct? Yeah. Now I want to say target of PTR is equal to a double number. That's where I'm going to hit the wall. How the compiler is supposed to know here that when I say target of PTR, it's this that is executing, right? How does it know what is this? 2 seconds ago I was pointing to an integer. Now I'm putting a double. How does it know what is the size of the target? It doesn't know. It doesn't know. It's supposed to overwrite 8 bytes, 4 bytes, so this cannot happen. I didn't give it enough information. My design is bad at the beginning. I cannot just say pointer. What I need to say over here is to say it's an integer pointer PTR. So it knows what is it pointing to. When I say 1081, 1081 what? Room 1081? Or the seat number 1081? Or bus route 1081? What 1081? I need to know what that 1081 is. Are we good with this? Are we okay? Now, having said that, now I can actually say address of something, put stuff in it, and everything works. And if I want to actually access the double, then I create a second pointer, dptr, that is a double pointer. When I say that double pointer points to dvar and I put the target, it knows the target is double, therefore it can put the value, it can access it, and all the good stuff is happening. Are we okay with this? Yeah. Let's test it. So from what I said, I can actually write over here something like integer var, correct? Is equal to, or integer var. Then I can say integer pointer, PTR, correct? And I can say PTR is equal to target of. Oh, no. PTR is equal to address of var, correct? That's right? Is that right? Yeah. Now I can say target of PTR is equal, target of PTR is set to 1, 2, 3, 4, 5, right? Now I'm going to say C out var, and if what I said is right, var should be 1, 2, 3, 4, 5. Is that correct? So let's compile and run it. Ta-da! So why the devil they didn't tell you about that PTR and address of and stuff? The reason is that people who designed the language didn't want, like at the time that they were designing this language, they were languages you're not that old to know, called COBOL, things like that. It was so descriptive that it would take 3 hours to write a for loop in it. You have, could you please repeat? You literally had to write English. So they completely went the opposite side and they created C language, 4 I's. It's very cryptic when you're saying something like that. Because of that, they said, we're not going to do it this way because where's the thing? Where is it? Here? Okay. So they said, we're not going to say pointer. What we're going to do, we're going to represent the pointer with an asterisk. So essentially, integer pointer PTR will be integer asterisk PTR. But you should never call that asterisk. When an asterisk comes after a type, it is integer pointer PTR, double pointer DPTR. Don't call it an asterisk. Then they said address of is too long. Let's represent it with an ampersand. So when you say DPTR is address of the var, not ampersand the var, never say that. DPTR is address of the var. But to make it even worse, they say target of is asterisk 2. So, but target of comes before the name of the pointer. So when you put asterisk before DPTR, that means target of DPTR is this. Never say star DPTR. So to actually make this thing kind of understandable, target of and pointer, they're both asterisk, right? If the asterisk comes after a type, it means type pointer, like integer pointer, double pointer, employee pointer. You never ever say double star DPTR, double pointer. If it comes in front of a variable as a unary operator, like -5, +3, like a unary operator, that means target of, which essentially means A is equal to target of P, target of T is equal to X, A is equal to B multiplied by target of C, A is equal to target of M multiplied by C multiplied by C. Therefore, when you look at the asterisk and you go, ah, life is beautiful, that's multiplication. If you see the asterisk coming after a type, that's type pointer. If you see the asterisk coming as a unary operator before a variable, it means that variable is a pointer and you are saying target of. Capisce? Now, how did my program work? So if I'm saying all this, how the devil that thing worked? Look at this, pointer.h. What did I do in there? Let me add it in here so you can see. I tricked you. I said whenever you see target of, replace it with asterisk. Wherever you see address of, replace it with ampersand. Whenever you see pointer, replace it with star, with asterisk. Done. All you need to do is to say it right and it fits. If you read the language cryptic, it's going to be cryptic for you. You're not going to understand it. Say it right and it will fit right. That's what pointers are. Are we okay with this? Okay. I have 7 more minutes and we're going to go to the next step of the pointers. Water. I don't need coding anymore. And I can't talk anymore. Soon I'm going to lose my voice. Okay. So where did I go? Where did I go? Okay. Now we need to use, we need to understand when pointers are actually used. We talked about what the memory is. And we said when you actually create a variable, the variable goes somewhere in memory, right? And then you can create a pointer, and you can make the pointer point to it, and all the good stuff, right? And then you set, when you say target of PTR is something, you set it, and these are all what the pointers do, and so on and so forth. But what happens when you create an array? What is an array? When you create an array, when you say int AR5, there are actually 5 integers created back to back in memory. Contiguous, back to back. It's impossible for half of an array to be somewhere and the other half somewhere else. That understood? Next. You use indexing, so you essentially say A3 is 2, 3, 4, 5. They told us when they say 3, it's actually 4, because the first element is indexed as 0, unlike normal indexes, right? Or indices. But what happens behind the scene is actually this. When you create 5 integers, it's actually 5 integers and a constant integer pointer. And that integer pointer actually points to it. So this is what happens behind the scene. When you create an array, the number of variables that you want created with a pointer of that type pointing to the beginning of it. And because of that fact, if you say target of AR is 2, 3, 4, 5, actually this first element will be set. And that's where 0 comes from. Because AR is pointing to the beginning of the array, when you say AR 0, it means from that address go 0 integers further, which means the first one. Go 1 integer further, it goes the second one, and so on and so forth. And that is what is different between a pointer and an unsigned integer. When you have an integer, you add 1 to it, what will be added? 1. When you have a pointer, you add 1 to it, the compiler will look to see what type of pointer it is. If it's an integer, what is the size of an integer? 4. So 4 will be added. You say 1, it will add 4. If you add 2 to it, 8 will be added to it. If it's a double, you add 1, 8 will be added to it. If it's a structure with 10 doubles in it, 80 will be added to it, depending on what is the size of the target. And that's why when you actually say A2 is 444 and set it like that, you can actually say it this way. You can say target of AR plus 2. So you're essentially saying that address plus 2, because it's an integer, 8 will be added to it. Target of is 555. It works the exact same way. And this is called pointer notation of an array. And that is why when you pass an array to a function, you don't know what is the size. Because you are essentially saying, this is an array that is pointed by this pointer. Now I'm going to have a second pointer pointing to the beginning of it. It doesn't know what is the size. It just knows where it is. That's why you have to pass the size too. And that's why interchangeably you can say integer AI square bracket to pass it to a function, or you say integer pointer. They both work. Because arrays are essentially a pack of memory pointed by a single pointer. And that is it. Okay? That was an IPC 144 pointer thingy. And I wanted to clear it for you before we go to the next thing, the next day you are coming in. I can actually teach it in 3 minutes, but I think your head's going to explode, so I'm not going to do that. So, please.
Really beautiful. Thanks for that.
No problem. So please go through all these things. And please, I beg you, remember curve of forgetting? Did I tell you about a curve of forgetting? A very, very important research was done long time ago in a galaxy far, far away about how humans commit things to their long-term memory. For a 1-hour lecture, same day, you should review it for 20 minutes. After a week, review the exact same thing for 10 minutes. After a month, review the same thing for 5 minutes, and it's committed to your long-term memory. So don't be lazy. You finish this, you go home, for 20 minutes, quickly go through the code that I have written. Or go on YouTube, or the micro Teams that we have. YouTube, I haven't posted it yet. But go on Teams and make it fast forward, like 4 times. It talks like that. Go through it quickly. Just listen to everything very quickly in 20 minutes and set it aside. A week passes, for 10 minutes, just browse it. And then 5 minutes, just look at the titles, and it's done. Please do that, okay? Thank you. Have a good one. All right. By the way, the slides are in the notes too, okay? The slides, pointers, everything. So you can revisit the slides too if you want to. Oh, I'm committing the wrong thing.
Does C have any C plus have any protections against terrorism or pointer addition? Out of range stuff? The usual.
OOP244NAA.
Yeah, yeah.
345, not now.
They get some
OOP244NAA.
Is there a hexadecimal feature? Or just it just does it in the hexadecimal where it just memorizes it and knows the place?
The problem is that, give me a second, let me